Hi everyone, I'm Yunyi from MIT.
I'm Zeng, also from MIT.
Today, we will introduce lenticular objects, which are 3D printed objects with lenticular lens surfaces that can change their appearance depending on the viewpoint.
Many of you might have seen this type of lenticular cards before. They allow people to see different image patterns from different viewpoints, and they are widely used in arts and advertisement. For example, this gift card that displays a small tree from a lower viewpoint and a larger tree from a higher one. And we were wondering if we could apply a similar effect to the surfaces of 3D objects, so that not only 2D cards, but also 3D objects can reveal different patterns from multiple viewpoints. First, let's see how lenticular effect works on traditional 2D cards of flat surfaces. Those cards or surfaces are normally covered with tiny lenses like this one. Each lens has an underlying color pattern. For example, this particular lens has a red dot on the left side and a blue dot on the right side. If an observer looks at the lens from its left, the shooting rays out of his or her eyes will be refracted onto the blue dot, so that the entire lens will show up as blue. If this person moves to the other side, the rays will instead be directed to the red dot. In this case, the entire lens will show up as red. This is how one lens reveals two different colors under two viewpoints. Together, all the lenses with different underlying colors or patterns can create lenticular effects like this one here. In our research, we applied the similar concept to 3D objects, such as this AirPod case with pattern shifting effects. And this kettlebell shell that helps to correct users' body pose during exercise. It shows an upward arrow when the user's arms are too low and a downward arrow when they're too high. The users will only see the check mark when they lift the kettlebell to the recommended height.
Our system has two contributions. First, a 3D editor that allows a designer to generate files for lenticular objects. And second, a fabrication pipeline that effectively fabricates such objects. I will demonstrate them with the kettlebell shell example that we've just looked at. To make this kettlebell shell, I first import the shell object from the files. I then set up a viewpoint. And I move it to the correct location in the viewport on the right. At this viewpoint, the kettlebell is at the correct height, so I assign it the checkmark image. Now that I have set up all three viewpoints, I can then preview the appearances from different angles. The lenses and color pattern are then generated automatically. So I just show you the editor for creating the lenses and color pattern. Now let me talk more about the fabrication pipeline. After making the 3D models, users can fabricate their objects. In the case of the kettlebell shell example that I've just created, I first use a renderer to preview the lenticular effects. I then 3D print the object, the lenses, and the color pattern all in one pass. After that, I coat the 3D printed lenticular object with 3 layers varnish. And here's the result. Upward arrow, the downwards arrow, and the check mark. So before I dive in more to the fabrication parameters, let me briefly zoom out and talk about the lens geometry. To prepare for the best final result, we need to balance 2 factors. First, we need to minimize the height of each lens. If a lens is too tall, it will stick out too much from the original object. And second, we need to maximize the number of viewpoints that each lens can support. To find a good balance between the 2 factors, we've calculated how different lens parameters affect the size of the largest image spot, which is inversely related to the number of viewpoints. We then plotted the relation between the image spot size and the lens's base height. And we then selected the point mark in the plot, which gives us both small lens height and a large number of viewpoints. If you're interested in more detail on the lens geometry calculation, please check our paper. As a result, our selected lens geometry supports 19 viewpoints. Here, we back it up with the rendered image of the same lens showing 19 different colors. This, however, is a theoretical value, and it assumes that the lenses are fabricated perfectly. In fact, the fabrication technique still has limitations, and the lenses we fabricate typically don't have such perfect surfaces. Therefore, our next step is to find the smallest lens size that we can realistically fabricate. We first tested the printable resolution of the underlying color pattern, and we then tested various lens sizes and post-processing methods to make sure the surface quality of the lens is acceptable. According to our results, we recommend using lenses with 3 mm diameter and post-process it with art varnish. Showing here are the best results we can currently achieve. We can see that the best fabricated results are still not coming close to the image quality of the rendered result. And thus, we conclude that the fabrication is still a big limitation, which might cause the fabricated objects to look different from the simulation. For some more use cases, we fabricated this nightstand that dynamically greets the user. For example, when I'm in bed, I have a lower viewpoint, and it will show me good night. And when I sit up, now I have a higher viewpoint, and it will show me good day. Another use case involves a pair of shoes that can cheer me up. When I'm having a bad day, I wear these shoes, look down, and see a cheer up message. But this message is secret, because when other people look at my shoe, they look at it from the side, which only shows the standard shoe design. Our work is part of the larger vision of making objects with dynamic appearance. Prior works have used smart materials and integrated LEDs to achieve such goal, while our approach uses lenticular lenses to create different appearances from different viewpoints. In the future, we aim to find more approaches towards this vision. And for this particular approach, we plan to support dynamic lens geometries so that we have smaller lens heights and better viewing range. Thank you very much for listening to our talk, and I'm happy to take any questions.